Hello, and welcome to Smithsonian.com Nobel Prize 2014 predictions. We are coming to you from a variety of locations. I'm Victoria Jaggard. I am an associate web editor with Smithsonian.com in charge of our science coverage. We are joined today by Helen Thompson, who is one of our science reporters, as well as Amanda Yoho. Hi, Amanda.
Hello.
Who is at Case Western Reserve University and a blogger at Starts with a Bang. We have Andrew Grant from Science News. He is their physical sciences reporter. Hi, Andrew.
Hi, good to be here.
Charles Day, who is the online editor for Physics Today magazine. Hello, Charles. And Jennifer Ouellette, who is a prolific writer and author of several books and is currently with Cocktail Party Physics over at Scientific American. Hi, Jennifer.
Hey there.
All right, so we are talking today about who may take home the 2014 Physics Nobel Prize. If you out in the audience have any questions or predictions that you want to pose to the panel, please use hashtag #PhysNobel. So one of the leading predictors in terms of recognition in the world of trying to prognosticate the physics, or all the Nobel Prizes really, is the Thomson Reuters, what they call citation laureates, where they are looking at data about who is being cited in the scientific literature to try to see who's having the most impact across a particular field. Charles, how are we feeling about some of these laureates?
I'd first like to point out that using citations to assess importance is tricky. One reason is that you can get a lot of citations if the subject you're working on is easy for other people to work on, and they can write a paper. So it could, it's going to miss something like the discovery of super heavy elements, where there are only 3 labs in the world that can do that. But that said, if your work is cited by other people, they think it's important. So if I remember correctly, Thomson Reuters went for discovery of topological insulators, which is a weird kind of electronic state in some materials. The LED, we all know what those are. Well, actually, it was the organic LED, I think. Those are the plastic glowing things on cell phone screens, and the nanofiber laser.
Great. So talk to me a little bit more about topological insulators. What are these exactly?
Well, forget the T word first. An insulator is a material that does not conduct electricity. The electrons are locked inside their atoms in the material. Now, a topological insulator has a way around that problem. So the bulk of the material is still an insulator, but on the surface there are some channels, if you like, where electrons can whiz along, and not just any electrons. When they whiz along, they go in, they're like little magnets, and their spins are ordered. So some of them are pointing up, and some of them are pointing down. And the ones that point up will go in one direction, and the ones that point down go in another direction. Now, why are they called topological? Well, some people don't even think they should be called topological, but what's going on is that the structure of those channels I mentioned, those can be, if you like, deformed. You can play around with some of the properties of the material, but the topology of those channels remains the same, and the channels still exist.
Okay. Now, how does the rest of the panel feel about that particular pick? Does anyone have any thoughts on how realistic it might be, or how worthy?
Well, I'm intrigued by it because I love materials physics. But a few years ago, there was a Nobel Prize for graphene, which was the 2-dimensional version of essentially graphite. And it was a tremendous achievement just to even make this stuff in the lab. But there was a lot of feeling I felt among physicists that it was a little premature, that the huge potential that graphene had was never fully realized. And so I guess my question is, when we're talking about topological insulators, it's not necessarily that it's not an incredibly important advance. It's, is it too soon? Will it generate the same amount of controversy? And I guess, Charles, since you've covered this, recently, maybe you might know what some of them.
I'd like to quote Andre Geim, who discovered graphene. He wrote an article about the material for Physics Today, and whenever someone would ask him what's the use of graphene, he'd say, well, imagine you're on a cruise ship and you see a school of dolphins, and they look beautiful. Asking what uses graphene is like asking what do dolphins taste like. So I think in the case of topological insulators, they are so interesting that even if there's no application, they could be a deserving winner.
So what do you think was the reason behind all the controversy over graphene?
I think there were some researchers who believe they might have been included. And graphene, if you look in the literature, you can find papers going back decades before the discovery. So in a sense, what Geim and Ouellette did was discover an easy way to make the material, not so much they didn't discover the material. As for the controversy, I didn't actually cover it. I don't know that.
Yeah, this is an interesting concept, the idea of somebody winning too early in a Nobel Prize, because as I understand it, the Nobel Prizes, this is the rock star moment in science. This is when everybody perks up and pays attention and wakes up all the journalists super early in the morning to be ready to cover this event. Andrew, can you talk a little bit to us about the importance of the Nobel Prize to science and to scientists?
Well, it's a good question, separating scientists with the general public. For a scientist, it's in some ways the ultimate honor. In some ways, it's kind of a strange award because a lot of times you're awarded the prize decades after the work that you did to deserve it. I mean, topological insulators, we're talking about something that was discovered a couple of years ago. But last year, the winners for the Higgs boson, they had made their predictions in the 1960s. So in some ways, it's kind of a strange award, and you kind of wonder, should we be giving these awards to people decades after, when the money won't necessarily help them do new cutting-edge research? But on the other hand, it's really the history behind the award, the kind of secretive way that they do it, and the way that we're sitting here right now with no idea who's actually going to win, but we can come up with some fun ideas. That kind of makes it very exciting.
Great. I had the opportunity a couple of years ago to attend a really awesome meeting that was the Lindau meeting of Nobel laureates. They brought together 500 young researchers from around the world, and they invite all of the living Nobel laureates. The year that I went was physics. And each laureate just gives a half-hour talk about whatever it is that they want to discuss, and then you get to hang out with them. So I agree that the prize is really interesting in that meeting everyone at this meeting made me realize how much someone that I work with could have been one of those people, or could be one of those people. I have faculty members here at my department recently who were working on a cutting-edge dark matter detector. They one day could be part of an experiment that eventually gets a Nobel Prize. And that sort of possibility of interacting regularly with somebody who might make these groundbreaking discoveries that end up being the people that get announced is really exciting.
Wow, that sounds like an amazing meeting. Where does that take place?
In Lindau, Germany.
Okay.
It's every year. So they cycle through the chemistry prize. They go through all the prizes, and then one year they have just sort of a mixed bag of people that they invite. But yeah, it was a fantastic opportunity.
And they really just get to talk about whatever they want? Could they give a half-hour lecture on Breaking Bad if they felt like it?
Yeah, actually, one of the most interesting points of the meeting is that we had 2 talks where two different laureates fell on opposite sides of the climate debate.
Ooh.
So that was very interesting to see. Yeah, with the one that's for noting that climate change is human-made, obviously coming down on the popular side of what everybody else in the audience was thinking too.
Wow, okay. So to get us back a little bit to our predictions, in addition to looking at the Thomson-Reuters, which Charles points out has its flaws, or at least isn't always the most reliable way to go, I was looking back at some of the records, and they have managed to successfully predict who would win the Nobel Prize in Physics 4 times in the last 10 years. So I don't know how that counts as a track record. Who else do we think is a possible? Who would you guys like to see win? Jennifer, why don't we start with you?
I was intrigued by the predictions. I think that one of those 3 that they mentioned might be likely, if the committee, because we can't read their minds, if they decide that they want to give it to something in the materials or condensed matter area. So I kind of, when I look at my picks, I'm kind of looking at other stuff. I kind of want to go a little further afield. And the most obvious one, if we're looking at, say, basic quantum theory, would be Wojciech Zurek. He's a Polish physicist. He's done a lot of important contributions and just some fundamental ideas in quantum mechanics. Probably the most notable and easily accessible for a lay audience would be this notion of decoherence. It kind of relates to this notion of do things, the notion of the observation problem in quantum mechanics. Why? I think Einstein once famously asked Niels Bohr if he thought the moon didn't exist when you stopped looking at it. So the notion of decoherence is basically a way to explain why classically at the macro scale we don't see some of these quantum effects. That essentially it's those interactions that break, say, entanglement between things, but and basically interfere with quantum states, and that's why at the classical level you don't see some of this stuff. So that alone is just a really fundamental aspect. He's also got other things like the no cloning theorem that's been very, very important in quantum information theory. So he would be probably my top pick if they go for something a little more esoteric. And I know that a couple others will agree with me that it would be nice maybe to see a woman win, because the last time a woman won, I think, was in the 1960s. So my picks there would be Wendy Friedman, who's an astrophysicist at the Carnegie Institute for measuring the Hubble constant, and the perennial dark horse favorite Vera Rubin, who predicted predicted dark matter in spiral galaxies. The issue there being, I can't believe Vera Rubin hasn't won yet. Dark matter, there's actually quite a bit of evidence now, indirect, that it really does exist. And if they're waiting for direct detection, that could be a while. And I guess my concern there is, A, Vera Rubin would die, therefore be ineligible for the Nobel Prize, or B, the focus would be so much on the direct detection that she would be shut out. So I would like to see Vera Rubin win at some point.
Yeah, I completely agree. And I think that even if it turns out that we don't get direct detection evidence of dark matter anytime soon, the fact of the matter is her research so fundamentally changed the way we think about the universe and what has been in the universe that we know, even if dark matter doesn't happen to exist, we have to modify gravity in some way to explain the galactic rotation curves that she found. So regardless of how things shake out or what we end up finding in the universe, her research was central to pointing us in the right directions. So I agree. I would love to see her win, and I don't understand why it hasn't happened yet.
She's still on my dark horse because, she hasn't won yet. So maybe they could surprise us.
And there's another thing in Vera Rubin's favor, and that was the award of the prize to dark energy, which I didn't predict because I thought dark energy was a question, not an answer. And as Amanda points out, we don't know what dark matter is, but we know there's something we don't understand about the universe out there.
Yeah, that's an excellent point. How frequently, is it a rule somewhere in the Nobel Committee that you have to have a direct, tangible evidence of a prediction in physics?
I don't think it's a rule per se. It tends to be a good rule of thumb. You know, generally, it's one reason I think why, you know, Alan Guth and others haven't been honored yet for inflation theory, because they're waiting for some direct detection to kind of back up the theory. You might argue, I agree with Charles. That's why I think the dark energy was surprising, but at least there was a direct observation of something that had tremendous theoretical implications. And I think when you're dealing, you know, let's face it, if you're a woman, you basically have to be twice as solid in order to get this. I think that's just a reality.
Hmm.
Yeah, I think there's a fundamental difference though between awarding for something like inflation, which is a theory that we're still waiting for a lot of information about, and something like the award for dark energy was really the award for measuring the accelerated expansion of the universe. And that's something that's indisputable. We measured that. We know it exists. There's no question. Now we have to figure out what's causing it. And that's the same thing with Vera Rubin's discovery. She measured it. We know it's there. And if the Nobel Prize is given for the largest impact in physics, I mean, her research has had incredible impact on the field of astrophysics and cosmology.
Yeah.
Great.
So the mystery deepens.
Yeah. So just to remind anybody, if you're tuning in just now, that if you have any questions or predictions that you want to share, please go to, let's see if I can get this right, #FizNobel hashtag on Twitter, and we will try to get to you as quick as we can. Andrew, did you have any other predictions that you wanted to talk about for, you think, likely picks, or perhaps someone you'd like to see win but you may not? Sure.
I'm going with a guy who I just think deserves to win and has not won yet, and that's Charles Bennett from IBM. And you know, he could get the award along with people like Gilles Broussard and William Wooders. And basically, what he did was predict or give a way to achieve quantum teleportation, which isn't quite as cool as Star Trek, but is pretty darn cool. And that basically says that if I have this particle, and according to quantum theory, it has multiple properties at the same time. If I measure it, I ruin this delicate quantum state. Yet in this kind of, it's a complicated way, but in a way, well, pretty simple. A combination of some quantum tricks and just you know, a regular phone call to send you some information, I could get you a particle that you have to take on the exact same state as the particle I have. And you know, he predicted, he set this up in the 90s, in the early 90s, and now we have experiments done in Switzerland where they're teleporting particles over about 100 miles through open air. So quantum teleportation is this fun thing, and it's could be very important for future quantum communication, cryptography, and computers. So I think that's something that I think he's long overdue for a Nobel, frankly.
Andrew, I have a question. I mean, it's true, like, isn't it true in recent years that it's not even just single particles? There's actually like clouds of particles that they're able to teleport.
Yeah, I believe you're right for that, and it's getting more complicated all the time, and they're doing more and more amazing things. And you know, it's one of those things where we don't have quantum computers yet. We don't have.
D-Wave says we do.
That's true. That's true. But you know, it's one of those things that clearly is spurring a ton of research, and I think it's deserving.
Okay, well, we have a question that's not 100% Nobel related, but it's definitely physics, from one of our viewers. Helen, would you like to do the honors?
Okay, so this is from @PeoplesAtheist, and they're wondering, through gravitational lensing, could we theoretically be looking at something that is located behind us? So I'll open it up to the experts.
I was going to say, Amanda, you got this.
Yeah, no. Gravitational lensing just means that anything that's Well, it depends on what you mean by behind us. I mean, we have things that are looking out into space all over the place, so I'm not sure exactly what they mean by behind us. But gravitational lensing just means that you have some really massive object, usually a galaxy cluster, and there's some bright object behind it, and the light's shining all over the place. But once the light comes past close enough to this really large object, the light gets bent around and focused towards us. So really it just means that there's some massive object that's using its gravity to focus the light from some background object. And that's what gravitational lensing does for us. So it's always sort of along the line that we're looking, whether I don't think that behind is the correct terminology to use, but you know, with telescopes we're able to look in all different directions to find the gravitational lensing events.
Actually, my guess about the question is could you imagine a gravitational lens that is so powerful that light does a 180-degree trip around the object and comes back towards you?
That light does a 100.
Because the gravitational lenses that we know about, they bend light only slightly.
Right. Right.
Could a potential be so strong that the photon whizzes around and comes back to us?
Comes back to you. I don't think so. I don't think so.
Yeah.
All right. Well, let's see. So a little bit before we started the show, we were having a chat, and I believe we did talk about another potential contender in Nobel's having to do with neutrinos. Charles, did you want to take this one?
Yeah, that's my pick for this year. So neutrinos, the neutrinos were discovered in 1956, and then 8 years later, actually in 1962, a different flavor of neutrino was discovered. So it looks like a neutrino, but it's obviously different. And as soon as people started thinking about different flavors, they thought, well, could the neutrino switch flavors? And that was a theoretical possibility, and it was invoked later to explain why we don't see as many neutrinos whizzing out of the sun as we expect. And it turns out the answer is because they oscillate between flavors. There are actually 3 flavors. A third one was discovered in the 90s. And as soon as you have oscillations, it opens up the possibility that neutrinos have mass. And if neutrinos have mass, then you have all sorts of difficulty with the so-called standard model of particle physics. In fact, you might remember last year's prize was given for the Higgs mechanism, but the Higgs mechanism can't work on neutrinos as we know them. So you have to do something to get the mass for the neutrino, and there are all sorts of ideas out there. And neutrino oscillations and the physics about them is a good place, some people think, to look for the origin of why there's more matter than antimatter in the universe. So neutrino oscillations are very important, and they were first detected in Japan in a big experiment in the Japanese Alps called Super Kamiokande. And the neutrinos oscillating from inside the sun, those were detected in Canada in 2001. So I would like to see the prize go to the 2 project leaders of those experiments, Takaaki Kajita of Japan and Art MacDonald of Canada.
Okay, we have a picture to share. Hopefully I can get this to work. This is what I believe the inside of Super Kamiokande looks like. You can see some people sort of rowing along on the inside.
Those are all detectors. Those are all like looking for those little tiny flashes that would amount to detection. It gives off this little burst of light, of radiation, and that's what they pick up. And it's really hard to do. That's why they need so many of them.
Right. So trillions of neutrinos are passing through us at this moment. Barely any of them interact with anything. But when you have a detector that big, every now and then a neutrino is going to strike and cause a flash of light, and that's what those detectors pick up.
Something like 6 or 7 events, like out of billions.
Yeah, it's pretty incredible.
It's really small.
Wow. And how many neutrino detectors like this are there around the world at this point?
There's one, it's not a water detector like that one, but there's one at the South Pole right now that they've actually used hot water drills to drill into the Antarctic ice to put detectors in there and use the Antarctic ice as the actual detected material.
Yeah, it's actually called Ice Cube, which was very clever, I thought. And I think in Chicago, I think Juan Calar and some other people are trying to use old-fashioned bubble chambers and things like that to detect. Probably with less likelihood because they're smaller, but it's a way of trying to revamp old technology to a new thing. So it depends on what you mean. I mean, these really big underground experiments are really expensive and large, and there's very few of them. But you've got these smaller attempts as well.
Okay. Now, Charles, this also raises an interesting point that I wanted to pose to the whole panel, which is one of the issues, I guess, with awarding Nobels in physics is physics collaborations can be massive. Mm-hmm. Hundreds upon thousands of people that we're talking about who are involved in any one important discovery, the Higgs being an excellent example of that. How do you feel about the concept of the award then just going, I believe the Nobel Committee places a hard stop on 3 people.
Yeah.
How are we going to get around this?
Well, I don't think they can. It's a very difficult problem, and it's possibly why it's difficult, if not impossible, to give the medicine prize to the Human Genome Project, or both of them. I don't know the details of the organization of Kamiokande and Snow. I thought, frankly, that neutrino oscillations was so important that they ought to get a prize, and I just picked the 2 head guys, but that's not a really just great way of going about things.
I think it gives a misleading impression of how science is conducted these days also, especially in astrophysics and cosmology. I mean, these results aren't brought about by 2 people. They're brought forth by hundreds of people that are working together on these incredibly impressive experiments. So distilling that down to 2 names, I think is pretty misleading.
It's an example of how I think when the Nobel Prizes were established, I think it was much more common to have 1 or 2 people, and science has really changed, as Amanda says. So I don't know what it would take. I mean, do we need to change the rules of the Nobel Prize? Is that even possible, given the stipulations in the endowment?
So, for example, would they ever allow an entire organization to take home a win as opposed to a single individual?
Right.
And I was talking with a few colleagues about this topic the other day, and something that someone brought up was what happens if an experiment is disbanded and someone wants to give them the prize much later after the experiment has concluded. Then how do you decide? But I think those challenges aren't reasons to not change the way things are awarded. I think that to stay relevant, the Nobel Committee needs to figure out what to do in the future.
Great. All right. And just again to remind anybody who's just tuning in that if you have any questions for the panel, we're looking at #PhysNobel, or if you have any predictions that you would like to share with us and get some thoughts on, we'll be happy to take those too. Helen, do we have anybody else who has some questions for us?
We did have a question from Carmen Jal over at Chemistry and Engineering News. She was wondering, historically, has there ever been as obvious or inevitable a prize as the Higgs seems to have been?
Yes, the discovery of high critical temperature superconductors. That resulted in the Nobel Prize, or maybe the next year.
Yeah, it was the next year.
What exactly is that for more of a lay reader?
Andrew, do you want to handle that one?
Sure. So previously, going back to about 100 years ago, actually, there was discovery of superconductors, which are materials that conduct electrons, whisk electrons around with basically no resistance. They perfectly move them around with no losses. The catch, though, is that you need to do it at just about absolute 0, which is the coldest possible temperature. But in 1986, 2 researchers basically found this new class of materials that involve copper and oxygen that had this superconducting properties at higher temperatures, still, negative 400 degrees Fahrenheit or something around there, but much higher than before. And the ultimate hope is to get to room temperature so we can, whisk around energy from power plants around with no losses. So yeah, that was discovered in 1986, these high-temperature superconductors, and it won the Nobel the following year. And speaking of that, it is possible that a new class of materials that are superconducting, iron superconductors, that might win a prize soon as well.
I was going to ask, what about the Kobe measurements back in the 90s, where they actually mapped the cosmic microwave background radiation, and it fell perfectly along that black body radiation curve? I mean, that was something that got a standing ovation when it was announced at a physics conference. It was one of the first times I actually really saw that level of excitement over a result. And I think it got a Nobel Prize within a couple of years. So that might be another example.
Okay. Well, this leads us to the interesting elephant in the room when it comes to talk about physics prizes. I know you all know that I'm going to say gravitational waves. And how are we feeling about the current situation with BICEP 2?
Well, look, if the Planck data had come out and even verified a smidgen of BICEP 2, I would say that that would almost be a shoo-in for this year's Nobel, but the fact is it's looking kind of bad. It's looking like it might, in fact, is a very, very interesting, very delicate, sensitive measurement that I think is an incredible achievement on its own. But now I think there's some political, pushback on that. It looks like what they really actually measured might have been cosmic dust, and that case is looking stronger than ever. We won't know for sure until the two teams actually combine their data, but I think that they're even beyond being a dark horse candidate for this year, which is too bad because I was kind of rooting for inflation. I would like to see some, we all really, really would like to see something like that happen, but I don't think this is the year.
Yeah, I agree, but I do think that when someone does pin down primordial B modes, that it will be a shoo-in, I think. And I also think, because, Kobe gave us the first black body spectrum, and then WMAP gave us the first power spectrum of the cosmic microwave background temperature fluctuations. And it won a Nobel Prize, I think, relatively shortly after its data release also. So I think there's pretty strong evidence that perhaps when Planck eventually releases its full sky polarization measurements, that there's some precedent, at least, for that type of result getting recognized with a prize.
Okay.
But they haven't done it yet, right? They haven't released the full, yeah.
No, they haven't.
And Amanda, just for people who aren't as familiar with the backstory here, can you talk to us a little about what you mean when you talk about CMB polarization?
Oh, sure. Okay, so the cosmic microwave background is light that's coming to us from shortly after the Big Bang, just under 400,000 years after the Big Bang. And because of the way that things were interacting with each other before the formation of the CMB, light couldn't really travel all that far. So the moment the CMB was formed is really the first thing that we can see with optical measurements. We can't see any earlier. So the way that the light has little patterns in it, we often call them temperature fluctuations because you see these patterns of hot and cold spots. Those things tell us about a lot of stuff in the early universe, like what we think the dark matter content is, what the curvature of the universe could be. It has a lot of information. And in addition to these intensity measurements, the hot and cold spots, it also seems to have some preferential orientation. So since light's a wave, it could be oscillating sort of like this, or it can be oscillating like this, and those have two different polarizations. So we're actually measuring, now what we're hoping to measure are these orientations of the incoming light waves, which already are, the cosmic microwave background has a uniform temperature of 2.73 Kelvin, so super cold. The temperature fluctuations are 10,000 times smaller than that, and the polarization on average is 10 to 100 times smaller than that. So we're doing incredibly precise measurements of the earliest light in the universe that we can see. It's an amazing achievement.
Mm-hmm. And that's what BICEP 2 did. Whether or not it turns out to be cosmic dust, they made that measurement, and that's just amazing.
Yes, exactly.
And Jennifer, the measurement that they were attempting to make, this is gravitational waves. Can you describe a little bit more about what we're talking about with primordial gravitational waves?
Well, I mean, gravitational waves are we're pretty sure we think they exist, but nobody's directly detected them yet. I mean, I think Amanda described it well. These little ripples in space-time that happen. If you think about banging a drum, for example, and then that sends out little shock waves or ripples. And what happens, the Big Bang probably would have had something like that. And the notion there is that it would have left traces in the cosmic microwave background in these tiny little fluctuations, these temperature fluctuations. So that's essentially what they're in the polarizations, essentially. So that's what they're trying to do. There are other experiments, things like LIGO, that are trying to directly detect gravitational waves, from other sources. But looking for it in the cosmic microwave background is a very specific kind of test of that, and it would be a huge, huge feat if they found them. And it would be very strong evidence in favor of inflationary theory, which is why it was such a big deal when it was announced earlier this year.
Okay.
And such a huge disappointment when it turned out that it's probably going to be cosmic dust. Yeah.
Right.
And if we eventually have direct measurement, I think, of gravitational waves through LIGO or the ELISA experiment, which is a space-based direct detection experiment for gravitational waves, I think that that's a pretty strong contender also. That would be a fantastic detection.
And in a sense, gravitational waves have already been honored with a Nobel Prize. Through
pulsars.
Pulsars, yes.
Right.
Where Joe Taylor and his student Russell Hulse discovered a radio pulsar that happened to be in a binary system, and by making very precise measurements they could deduce that the binary pulsar was losing energy because it was generating gravitational waves that were taking that energy out into space. And it is still shrinking.
That was also a missed opportunity, I think, for the Nobel Prize to go to a woman. Because Justin Bell worked on that experiment as well.
That's one of the biggest snubs, I think, in Nobel physics history.
It's famous, right?
Okay, well, that brings me to another potentially interesting question. What do we think, or who do we think in the past, who may no longer be eligible, perhaps because they are no longer with us, is someone who should have been a Nobel contender and sadly didn't make it?
The first one that comes to mind for me is Emmy Noether. I mean, the Noether's theorem is such a cornerstone of theoretical physics. It tells us that if there's some invariant thing in our system, so we have physics experiments, we know that they're time translation invariant, which means it doesn't mean if we start the experiment now or if we start the experiment 6 seconds from now, we'll get the same results. That translation invariance tells us automatically through Noether's theorem that energy is conserved. Like, it's fantastic. It's such a fundamental finding, and she was never awarded the Nobel Prize. I think that's really shocking.
I would probably say Clyde Cowan. He was one of the people that was involved with the neutrino work that Charles mentioned earlier, and he didn't share in that Nobel Prize because he was dead, but he certainly would have been among those included.
Okay.
And there's Lisa Meitner, who was the co-discoverer of nuclear fission. The prize went to her, I suppose, her boss, Otto Hahn, who didn't really understand what he discovered. And we should also remember Ernest Rutherford, who should have been awarded at least one other Nobel Prize. He got it for discovering a kind of radioactivity, but he also discovered the atomic nucleus and the proton.
Right. Mm. He would have liked to have won, I think, a prize in physics as opposed to chemistry, given his infamous comments about other sciences.
Okay. Helen, did we have anything off of the Twitter stream?
Not at the moment. Let's see. We did have one comment just touching on Carmen's question from a while ago, suggesting that James Chadwick and the neutron would also be one of those where it was, you know, something like the Higgs, and it was immediately obvious that it was Nobel worthy. If you guys want to chat about that.
I actually have a question for Andrew, because he had mentioned earlier the tetraquark work. That's something that's kind of new and intriguing, and maybe he could tell us a little bit about that. I mean, I think it's a long shot for this year's Nobel, but it's really interesting work.
Sure. Well, so tetraquarks are interesting because quarks are these fundamental constituents of matter. And usually quarks come in pairs to make particles called mesons, or in trios, protons and neutrons, you know, inside the atomic nucleus. And recently they found this strange combination of 4 quarks. And you know, like we've been talking about, I think this is too early to award a Nobel Prize, and I don't, you know, it may not lead to anything that interesting, but the idea that all the particles we know about were 2 and 3 quarks, made up of 2 or 3 quarks, and now we're getting to 4, is pretty interesting, and we'll see where that takes us.
Yeah, that was actually one of the ones I thought was really interesting too, because not just not finding them, but we thought that they didn't exist, and it's been hinted at other experiments, things at Fermilab, and I think also an experiment in Japan had seen hints of these 4 quark particles, but it wasn't until the LHCb put out their very definitive result that this existed. Yeah, I think that that's a really interesting result, but I feel like since particle physics was kind of the focus last year, I think it'll kind of be overshadowed by other subjects.
Interesting. Is there a sort of historical record of the Nobel Committee sort of moving through the subfields within physics? Like, do they seem to prefer shaking it up every year, or are they really just going on what they think was that year's worthy winner?
I think it depends. I mean, obviously there's a backlog of things that are interesting work. I think that, I mean, who knows how prize committees think, but probably there is a little bit of an effort not to, unless there's something really, really obvious, like 2 years in a row, I would think they would try to mix it up a little bit, which is why topological insulators might actually be a contender, something in the materials realm, because maybe they decided it's time for something like that again. But, you know, trying to second guess a committee is very, very difficult.
Okay, I believe we have another question off of Twitter, or another suggestion.
Yep, so this is from John Travis at Science, and he's wondering if it's too early for perovskite solar cells to win. He thinks it's too early. I'm wondering what you guys think.
Does that tie in a little bit to, I guess, some of the ferroelectric devices that are mentioned? You know, it's one of the contenders that the Reuters mentioned. Those tend to use some of those crystals, so maybe it might tie into something like that. So rather than having a prize be specifically for those type of solar cells, maybe it might be for the kinds of materials that include that particular category. That seems a little specific to me. I think that the Nobel Prize likes something a little bit more fundamental, but maybe others can comment.
It's not so much. I think it's not so much fundamental, or other. If it's not fundamental, then it has to have a really big technological impact, like fiber optics.
Mm-hmm.
And do you think this particular type of solar cells would not fall under that category?
We don't know yet.
Oh. Okay. So maybe, possibly, not quite so much?
I think it might be a little early. Like I said, I mean, it might get folded into something more broad, like the ferroelectric materials. Although the focus there seems to be on their potential for random access memory. But similar materials that incorporate those kinds of crystals actually do show up in a lot of these ferroelectric materials. So it might actually just be that it gets folded into a broader category and gets, name checked along with everything else. As Charles says, unless it can be shown to have a truly revolutionary impact in a very short time, then for that specifically, it would be unlikely.
Okay. Interesting.
But perovskites are interesting purely for basic science reasons. They can be the host of all sorts of exotic electronic phases.
Mm-hmm.
So it's not out of the question that they might be honored one year just for that reason.
Right, but not specifically for the solar cell application unless that turns out to be, truly life-changing and, across the board.
Okay. So one of the interesting things that came up, and I don't know if y'all had a chance to see Chemical and Engineering News earlier this week, did their take on who might bring home the chemistry Nobel. And one of the issues that they raised with chemistry is they always seem to get hijacked by the biologists. Are there any fields that we think might hijack within physics, or that physics tends to hijack? Because I understand also material science, for instance, seems to straddle the boundary.
Yeah, physics tends to hijack chemistry too. Poor chemistry.
Because something like these materials for solar cells, for instance, may be something that could fall in either category.
And the Nobel Prize for quasicrystals, that could have been awarded in chemistry.
Mm-hmm.
And the super heavy elements. In the past, heavy elements have been honored in the chemistry side of things, but I think a lot of people working on them are physicists and call themselves physicists. And when they're discovered, they tend to be published in physics journals, not chemistry journals.
Interesting. Does the composition of the committee have any sort of influence over whether or not physics will swipe something from chemistry or chemistry will swipe something from physics?
I don't know. In medical technology, there's been some physicists or physicist-like people who've won. MRI, for example, or CAT scans. Come to mention it, I don't think ultrasound imaging has ever been honored with a prize.
Okay. So out of the, sort of circling back to the Thomson Reuters citation laureates, we covered the ferroelectric devices and topological insulators. Did anybody have any feelings about the nanowire laser, or why that might be worthy for a prize other than citations?
Yeah, they seem to be mostly focusing on citations because that is one of the most cited papers in the last 10 years, and that seems to be their primary thing. It's a tremendous achievement. It's not probably something that would immediately jump out at me as a contender. Charles, you might have some thoughts on this.
I think the general topic of applying a voltage to a little bit of material and it emits light, that's part of the family that LEDs and organic LEDs and diode lasers, that they belong together. So you could imagine a Nobel Prize bringing all of those together with maximum three winners.
Okay. Now, do we feel like the three-winner cap, we've already discussed the issue with collaborators, but if they decided that they'd rather keep honoring individuals as opposed to institutions behind particular finds, is there a chance that they could ever lift that three-person cap, or is that actually helpful in some way?
I think we need a Swedish lawyer.
It's tough because where do you set the limit?
It's a slippery slope.
Yeah, it really is a slippery slope. But it is a shame that every year you could talk to people who were snubbed in some way. I mean, I talked to this physicist Gerald Guralnick last year, who unfortunately passed away this year. And I mean, he predicted the Higgs mechanism arguably earlier than Peter Higgs did, but because of publication, when it actually got published and things like that, it came afterward, and he didn't get the prize.
Right.
So if there were a cap of 8 or something like that, maybe he would have gotten it. But it happens every year.
Well, and that was really interesting because obviously Tom Kibble was another one that kind of got snubbed because of the 3-person rule. And, I remember my husband, famous John Carroll, wrote this book about the Higgs boson and had this whole chapter on who should win the Nobel, who might win the Nobel. And he actually said that Lynn Evans, the guy who actually built the Large Hadron Collider, who coordinated the construction of the actual machine, should be honored for that. That's an incredible achievement, but it's probably not the kind of thing that would be sexy enough for a Nobel Prize selection committee. But you needed someone like him, or the damn thing wouldn't have worked. Yeah,
I completely agree. I wonder how much the cap will affect who gets the prize for exactly that reasoning. Since it's easier to give it to the person who laid down the theoretical underpinning, there are often fewer of those than the people who work on the collaborations that then eventually verify these things. Which I'm a theorist, so I'm all about theorists getting the prize. But it is a huge achievement to be a part of these detectors that eventually confirm the existence of the Higgs. Or if we do measure primordial B modes with a CMB experiment, will it be the people who worked on that experiment who get part of the prize, or will it be Linda and Guth for having some evidence for inflationary models? So I think that kind of skews where the prize ends up going, because it's much easier to give it to a small group of theorists than a large collaboration.
Okay. Now, we're coming down to the 10-minute mark, so we should probably start wrapping things up. I had one last question I wanted to pose to you guys, which is, are there any indicator prizes other than the Nobels that you think people should be keeping an eye on, in the same way that you look to the Golden Globes to get a sense of who might take home an Oscar?
Well,
Charles, what about some of the APS prizes? Are there any of those indicators?
Possibly, but APS has a lot of prizes. I mean, that's not a bad thing, but the ones that some people follow are the Wolf Prize that's awarded by Israel. That's anticipated some winners. And there's one called the Lasker Prize, which doesn't apply to physics, more to medicine, but that's been pretty good at sort of anticipating who might win.
Yeah, I was going to say that the Wolf Prize is usually a pretty good precursor.
Okay. And have those already come out for 2014?
That's a good question.
Something we should have Googled before this.
So I think one pair of winners of the Wolf Prize are possibly contenders for the Nobel Prize. That's Michael Berry and Yakir Aharonov for their work on one of the kind of quantum weirdness called geometric phase.
Called geometric what now?
Phase. It's a weird property where you can change something about a particle by taking it around a path that contains nothing. It just, don't ask me to explain it because I don't understand it.
That's always the case with some of these more esoteric prizes. All the science journalists are like, oh man, now we got to figure out a way to explain this incredibly abstract, esoteric thing at the quantum scale.
Last year was such a treat, wasn't it?
I know, it's like, we got this.
if we did this last year, we would have predicted it perfectly.
I know. It would have been a boring discussion, though, because it was such a good.
Yeah.
Well, we would have talked about what would happen next year. So
that's true.
All right. Well, was there any other big physics discoveries of this year that, while it may be too early for this year's prize, could be something we'd want to consider further down the line?
So word is that Planck's polarization is supposed to be out before the end of the year, and so that won't be eligible for this prize because it's in October. which is word on the street. That's been happening, for the last 8 months. So it could end up being next year, but I think within the next cycle it'll be released, and then I think it's a pretty strong contender.
What exactly is that?
That's what we were talking about earlier with the BICEP2. The Planck data was basically what kind of put the nail in the coffin of BICEP2, because it's a little bit more accurate reading of the polarization data of the cosmic microwave background. Yeah, and WMAP won a prize, I think it was in 1996. I could be wrong about that. Because of so WMAP was a satellite that measured the entire sky of temperature fluctuations, and Planck is another satellite that will measure the entire sky. It's already measured the temperature fluctuations, and then it will add to that soon full sky polarization for the very first time. So I think that's a pretty strong contender. And if it comes out by December, it will be the biggest news of the biggest physics story of the year, I would think, right, Amanda? Mm-hmm. Yeah, I think so.
And just to throw in a little curveball here, just for a little fun. I mean, if you want to go more straight up astronomy, exoplanets has not won a Nobel Prize, and you could argue that it's not. Not as hardcore physics maybe as some of these things that we're talking about. But I mean, when you look at all the amazing planets we're finding around other stars and the Kepler spacecraft and all those things, people like Michael Mayor and Geoffrey Marcy, who were pivotal in that first exoplanet discovery in 1995, I mean, they've spurred a ton of interesting research. And I mean, that captures the imagination like pretty much nothing else that we've even discussed today. So it's a possibility.
From a coverage standpoint, it's a gold mine. Yeah.
So would the prize be for something like one of the detection methods, for instance? It could be the radial velocity, as opposed to saying exoplanets are the reason you've won.
Right, that's true. You could talk about the radial velocity method, which they used to kind of sense that the star was getting pulled by the planet. By the planet's gravity. But Mayor is usually talked about as the main guy because he was the one to discover in 1995 the first planet around a star somewhat similar to the Sun.
Okay, and what was the detection method that he used?
He used the radial velocity method.
Okay.
And Geoffrey Marcy confirmed that planet detection, and then he used the transit method as well, which is looking for the little shadow basically cast by a planet when it crosses in front of its star, and that's what the Kepler spacecraft has used to find thousands of probable likely planets.
And I think Andrew's right. I mean, the significance there is that it launched an entire field, and it's now like one of the most active areas of astronomy research out there. So impact-wise, I mean, that's a huge impact.
Yeah, it also makes it easier to answer the question at parties by non-physicists, are there aliens out there? Now we can sort of say, well, we do know that there are other planets in our galaxy. We haven't found any M-class planets yet, but that'll come, I think.
Any what class planets?
M-class. It's a designation from Star Trek.
Oh, right.
It means a planet that looks like Southern California on its surface and has breathable atmosphere.
Sunny.
Excellent. All right. Well, I want to thank everybody so much. Amanda, Andrew, Charles, and Jennifer, thank you very much for your time today. I want to also remind people that if they want to keep the Nobel Fund going, hashtag #MedNobel, starting at, I believe, 3 p.m. today. You can go to this URL and see our colleagues over at Science News talk about the possibilities for medicine and physiology for the 2014 prize. So thank you very much, everyone, for joining us. And we'll see what we shall see when the prize is announced for physics on October the 7th.
See you bright and early.
Thank you.
Bye, everyone.
Bye.
Bye.